We'll be talking about LRO LAMP. LAMP is the Lyman Alpha Mapping Project. It's a UV imaging spectrograph on LRO. And we conducted a coordinated set of observations with LADEE. Great, this movie's playing. So this is not LAMP data, but we had a really good set of coordinated observations between LRO, LADEE, and the Artemis missions. And we all worked as a team to really do some fancy things. And this is one example of the LROC image of the LADEE spacecraft itself at one of the mutual closest approaches that we identified. And sort of the albedo of the LADEE spacecraft is shown with this overlay. And that's pretty fancy. And so I'll talk more about the LAMP work, but just want to share my thanks to all the operations teams on all three missions for all this close coordination. Okay, we've seen several slides now on sources of the exosphere, so I won't dwell on that other than to say, when we, for the non-experts, when we talk about different species, helium, argon, and oxygen and hydrogen, these sorts of things, each one of those has their own set of relative source processes in terms of relative importance of those source processes. And so it's a bit of a puzzle to understand for each species which process is the most important one, what's the second most important process for producing these species, different locations, different times of day, and these sorts of things. And so having all sorts of in situ and remote sensing measurements obtained all at the same time can help us unravel this puzzle and get to the bottom of these processes, and then go and apply our understanding of these processes to other places in the solar system. The species that the LAMP instrument measures the best is atomic helium. And we do this at the 58.4 nanometer emission line. This is a spectrum wavelength versus brightness. And we've seen this helium signal in our data set all the time. And it took us a while to convince ourselves that this was a native helium signal that we're seeing, because after all, we know that the sky is full of hydrogen atoms that reflect hydrogen light from the sun back onto the night side surface of the moon in permanently shaded region, and that's what we use to create our great maps of the surface of LAMP's primary experiment. The solar system is also full of helium atoms that similarly reflect this light, and there's a big sky background of helium signal at this same wavelength. So we needed to come up with an observing technique that we discussed in Stern et al. 2012, where we really had a smoking gun, where we stared at one point of the sky with our line of sight, and made one measurement as we crossed the poles, where we have a nice illuminated column of emission of any native species. And then we do a different spectrum with something that's pointed basically away from the moon and just measuring sky signal. And seen here in blue is the residual of that effect. And so armed with this understanding of our measurement technique of getting helium extracted at just a few Rayleighs here, we could go into our full data set and pick out those times of day when LRO passes from day side to night side and back again, when we're in this twilight region where we have a sunlit column of gas between us and the surface of the moon, but yet we're still observing the night side of the moon and don't really have a background signal to work with much at all, other than an albedo of this sky emission I mentioned. And we can do this extraction and average up our 12 orbits per day worth of measurements and plot them point by point, day by day. I hope you can see this. It shows it better on the side monitors. And we noticed early on that we see a step function when the moon passes into Earth's magnetotail. We've heard a couple of LADEE results that have mentioned this, but we published this a few years ago in Feldman et al. And sure enough, we have a nice steady decay of the helium exosphere abundance after entering the magnetotail, and then it restores itself afterwards. And we have a lot of days of year accumulated by now, a few years into the mission. And this messy plot at the lower right is just to impress upon you that we have these time of day data points for lots and lots of days throughout the course of the mission. And Jason Cook, a postdoc with Alan Stern, recently published an analysis of the variability of this day-to-day trend in our LAMP data set. And we have lots and lots of magnetotail crossings to go in and study with detailed models of how the helium exosphere responds. And that's a good thing. Looking at a plot of this variability of points versus local time relative to hours after local midnight in terms of number density plotted here, we see that the peak is around 2 a.m., 2 hours after midnight, and that's very consistent with what the LACE mass spectrometer saw on the moon. And Mehdi Bena showed their data peaking between 1 and 2 hours there after midnight, so it's very consistent. The densities we measure with LAMP are within a factor of 2 of the LACE densities, and given our uncertainties in our calibration at these EUV wavelengths, that's an exact match, basically. So that's great. But interestingly, when we look at the points that deviate from the trend beyond this 3 sigma limit, or at the 3 sigma limit, we see several events that are just above the normal trend. And while we've seen that there's a correlation between the solar wind alpha particle flux that strongly controls the abundance of helium in the lunar exosphere, whether it matches exactly or not is something we need to go through and look at for every single event. It's been postulated for a while that there could be a more minor secondary source of helium from the interior radiogenic decay of different products. So if we can find an event where maybe a moonquake or some internal seismic event released a big plume of helium into the exosphere at a given time, that'd be really powerful as a tool to understand that interior process. And so we're going to work with Jasper on the Artemis team and compare with the NMS results too, and try to do that correlative study now that we all understand this process better. We heard in Tony's talk, and I think we'll probably hear more in the next talk, about the LADEE mission giving us a new understanding of the importance of, or potential importance of, meteorite bombardments as a source of the atmosphere, and how episodic the exosphere could be in nature. And when you think about any given impact, it's useful to look at our measurements of the LCROSS impact plume expanding outward that we measured with LAMP, depicted here in this artist view. And we also measured it with GRAIL. And imagine, if you will, an exosphere created with just multiple plumes expanding outward and overlapping one on top of each other, and then sort of equilibrating into a more envelope of a bounded exosphere. So it's kind of an interesting new way to look at the lunar exosphere, I think, and talking more about these impact studies will be useful. So here's the LCROSS light curves that we obtained and published in Science way back with mercury, magnesium, and calcium species, molecular hydrogen and carbon monoxide species shown here. And then on the right are GRAIL A and B light curves. We see 2 spikes for both the A and B spacecraft, time delayed in terms of when they hit the surface there. This is mercury emission. We also saw atomic hydrogen emission coming out of these impact plumes, and those gases are moving faster, and their light curves are kind of overlapping more, is what we see here. And it's very consistent with how we understand the physics of these plume evolutions to work. And Dana Hurley's published some papers, and we're working on some more to do more detailed modeling of the physics that goes into this expanding envelope of gases outside of these impact events that we're learning from LADEE are probably really important for the exosphere overall. We would have loved to see LADEE in its death throes, in its final days, right at the impact. We kept waiting for it. Are you dead yet? Are you dead yet? We'd have these telecoms where we'd plan this. And some of you may know that there was a outreach effort, a nice game of roulette. Can you pick the day that LADEE will impact or not? And I was really excited. I thought we had the inside track on this bet, and we had all of our dates set, and we were going to do our fancy rolls with the LRO spacecraft to observe it, just like we had done in the past for GRAIL and so on. But LADEE went ahead and crashed a couple days early, so it was within the range that everybody thought of, but we just missed it. Anyway, so another important species that LAMP has shown itself able to measure through that LCROSS impact experience is molecular hydrogen. And what you see here is data extracted over months and months of time, millions of seconds accumulated, very rigorous, careful background subtractions of reflected light off of the surface on the night side from starlight. And what you see is red, a data point, and blue is a model of the molecular hydrogen. Molecular hydrogen has all sorts of quantized energy levels, and they're populated in different states depending on the density and temperature of the gas. And we can fit a model roughly. It's noisy, not the best fit around, but yet we still get densities that are consistent with upper limits from Apollo 17 UVS and also sputtering models by Wirtz et al. Shifted around a little bit on me. But H2 is an interesting molecule because as a proton comes in from the solar wind, interacts with rocks on the surface, this is one of the mechanisms that we think of as possibly forming the water molecules that migrate diurnally on the day side of the surface, as several instruments now have all measured. And so this process also forms H2 molecules in the same way that H2 was formed. And so maybe if we can understand this potential source for the H2 that we're seeing, we'll learn more about this formation of water process that we're all curious about now. Okay, we've measured lots and lots of other species as well in terms of upper limits. And this is a table in Cook et al. Icarus, 2013, and everyone on the LADEE team should really be looking at this table of upper limits. We have this nice set of surface density limits that have really pushed down the previous upper limits by orders of magnitude. Almost all of these 27 different species are constrained more than what the previous upper limit had been. And so we need to go and compare notes with LADEE. One species that we're a little bit more optimistic about maybe sifting out of our LAMP data set next is atomic oxygen. And that would be interesting. There was a recent paper by Verberger et al. Where they used energetic neutral atom imaging to detect for the first time neutral atomic oxygen in the lunar environment. And their densities are coming in right about where we are, within a factor of 2 where our upper limits put us. So if we do a little better job removing some earthshine contamination that we're well aware of, maybe we'll be able to sift that out. And the LADEE measurements that Tony reported, I tried to scribble these down yesterday during Rick's talk, and I got them all wrong, I think, as I look at the numbers in Tony's plot. But anyway, his numbers were about 16, if I remember right in the same ballpark of this Verberger et al. So some useful cross comparisons there, and taking some of these tentative detections into real detections by working together is something we can do. Okay, great. All right. Argon has been a species that we thought for sure we'd be able to really say something new and innovative of when we launched LAMP, but it's remained elusive to us. There are a lot of instruments, systematic things that we've thought through, and the detector is just relatively less sensitive there. But we thought we had a detection that we reported at LPSC, and we called it tentative at the time, and we've done some more calibration work, and then it disappeared. And so we're withdrawing that. And today I just have new upper limits to set in terms of our measurement technique's ability to address this. But it's a puzzle for us because when we look at detailed models that match the late-stage data set, and we know exactly where we're pointing in terms of local time of day relative to just before dawn, just after dusk, we have these good expectations of what the density should be, and the LADEE mission matches those really well, but ours are much, much lower. So we've gotten a little smarter about how we do these comparisons, and we're going to focus in a little bit, thanks to some modeling by my postdoc Cesare Grava. We have this nice Argon model, and so we are going to focus more on the equatorial region where LADEE orbited and where the LACE existed, and we just extracted a subset of data around that space on the moon and divided it in dusk in red and dawn in blue times, and great. Still no Argon where we expected to be at this particular wavelength of light in the UV, but the good news is that there's some nice H2 quality signal that we're finding when we sift apart the data in terms of these latitude and local time locations. And so we're going to switch our emphasis to think more about the hydrogen molecule. Here are our upper limits. And again, these are a factor of 10 lower than what the expectation is. And so there's a real discrepancy here with our method compared to the LADEE method. And it's a puzzle for us. And as soon as we are really confident in our instrument characteristics, we're going to sort of close the loop and see what you all come up with on the LADEE team on this Argon question. In the meantime, like I said, we have some good handles on the H2 molecule, which has broad relevance, and we're going to keep working on that. All right, Tim Stubbs talked about our dust upper limit measurements earlier, so I won't dwell too much on that other than to say that at the particular times during the year when LRO was well situated to get this highly oblique viewing angle to measure dust and provide a new constraint, some of the best since Apollo. We tried some new observations with LADEE and coordinated very well, but at best we slightly shift that line a little bit lower, and we didn't see anything. But we all worked really hard to make that work. We did have some campaigns where we got smart about moving our line of sight right where we expect the argon to be. No signs of anything yet other than some nice helium signals. And lastly, we had another technique where we sort of, instead of staying fixed, pointed nadir, we slew back a little bit to increase our line of sight, slant path through the illuminated part of the atmosphere while still pointed at the nice night side surface. And we got some good signals there. Let me just go back and forward. We serendipitously caught the Earth in the LROC whack. And yeah, this is my last point. And it's really nifty that we saw the Earth passing through all three different color filters on whack. We could get a real Earth color image with the moon in the foreground. This is sort of true color sort of version of the LROC whack as seen with this particular geometry that we can use ahead in the extended mission 2 now. So lastly, we have this nice list of results from lunar exosphere studies with the LAMP instrument. The newer results to highlight are in bold here. We've seen flares of helium density at certain times that could be important for understanding internal outgassing. H2 molecule is something that is relevant and we can do a much better job on now. And we've pulled back on our understanding of argon and the detection there. So I'll end there. Thanks.
Could maybe take one burning, is it a burning question? Oh, yeah. Okay. But then we'll have to move on.
Why is it that helium is high on the midnight side?
Okay, so I always try to explain this and get it wrong, but it's one of these species that's thermally accommodated. So when a particle from the solar wind implants in the surface and neutralizes, it picks up the temperature of what that surface is. And so on the day side, when it's hot, it just has this much larger scale height, even if there is the same density of atoms there. And on the night side, it's colder. And so when we look through and measure it, it looks more dense from our point of view, I think. But if you looked at it from infinity and could measure it in vertical column, it would be similar.
In fact, the day side is so hot that you're continually losing helium because it's escaping.
Yeah, the orbits kind of bounce around towards the night side, yeah.